This video is about strength of conjugates. This is our second video in the 9.3.4 series. The one thing I should say is a favour for me is when you're watching these videos, if at a certain point something doesn't make sense, or you know at a certain point everything was fine to the 4-minute mark, but at 4 minutes you said this or did this and then it made no sense from then on, please let me know this stuff. I can correct these videos and fix them and put some clarifying information on there. So if you get to a point where something I said confuses you, please let me know. Send me an email, tell me what point that happened. Anyway, strong acids and bases. As we already know, a strong acid is one that's defined as being ionized completely to form H3O plus or OH minus. And because they ionize completely, the reverse reaction is very unlikely to occur. And because the reverse reaction is very unlikely to occur, that stuff we talked about a minute ago, those conjugate acids and conjugate bases, they will be very weak because the reverse reaction is unlikely, and therefore they're unlikely, those conjugates, to accept or donate protons. So the conjugate base of a strong acid is a very weak base, and the conjugate acid of a strong base is a very weak acid. So here's an example. We've got HCl plus H2O goes to H3O plus Cl minus. First of all, you should identify the acid and its conjugate base, and then tell me, is that conjugate base going to be weak, strong, or very weak? And the answer is, because HCl is a strong acid, its conjugate base Cl minus is a very weak base. It's effectively neutral. So chloride ions, when you see them in salts or in a solution, they'll have no effect on the pH. And there's one big idea here, and that is the fact that strong acids have very weak conjugate bases and strong bases have very weak conjugate acids. Next thing, weak acids and bases. Now we know that weak acids and bases don't ionize completely. They form an equilibrium with their conjugate. And because the reaction doesn't go to completion, because it's a reversible equilibrium reaction, that means the conjugate base of a weak acid will accept some protons to reform the acid, and the conjugate acid of a weak base will donate some protons to reform the weak base. And as a part of equilibrium, neither reaction goes to completion. So if you've got a weak acid, it won't fully ionize, and the conjugate base also won't fully ionize. So you've got both these situations. There's a nice equilibrium there, which means the conjugate base of a weak acid is a weak base, and the conjugate acid of a weak base is a weak acid. And so there's an example here, and I think I've covered up the wrong bit. There's the example there. It is acetic acid plus water goes to hydronium ions plus the acetate ion. Note for the weak acid and base examples, we're using these equilibrium arrows, and we can say that because acetic acid is a weak acid, that means its conjugate base is a weak base. Let's just go through why that is. First of all, we know acetic acid being a weak acid, it can actually donate protons. Not every acetic acid molecule will donate a proton, hence less than 100% ionization, but that means this is our acid. And what it becomes when it's donated as proton, this is the conjugate base. But because we know this is weak, and because we know it's in equilibrium, that means sometimes this conjugate base will actually accept protons from the hydronium to make the equilibrium reaction go back this way. And therefore, some of these acetate ions will accept protons, and some of these acetic acid molecules will donate protons. Therefore, because some of them donate protons, this acetic acid is weak, and because some of these acetate ions will accept protons, this is weak. So a weak acid has a weak conjugate base. So here we go, weak acid has a weak conjugate base. And a similar example down here, this time with a weak base. Now, ammonia is our weak base. It's our number one weak base example in the HSC course. And ammonia reacts with water to produce hydroxide ions and the ammonium ion. So we can say from that is because ammonia is a weak base, its conjugate acid, ammonium, will be a weak acid. And just like before, we know that ammonia can accept protons from water because it's a base, but we also know it is a weak base. And because it's an equilibrium, we also know that ammonium will donate some protons to hydroxide, and therefore it's a conjugate acid of ammonia, but it's a weak conjugate acid. Okay, so weak acids and weak bases have weak conjugates themselves because they exist in equilibrium. And the big idea from this page is this, that weak acids have weak conjugate bases, and weak bases have weak conjugate acids. So, this is the generalization. This is the big thing you've got to understand, the summation. So first of all, strong acids, what sort of conjugates do they have? Drum roll please. They have very weak conjugate bases, effectively neutral. So those weak conjugate bases have effectively no effect on pH. Strong bases. Strong bases have very weak conjugate acids, effectively neutral again. Weak acids, and note the equilibrium sign, weak acids, because they're in equilibrium, they have weak conjugate bases, and weak bases, because of equilibrium again, have weak conjugate acids. And that's the end of that video, and that one thing here is the one summation of this whole section.